So in this video, we're going to be going over multivariable functions and partial derivatives and the graphs of multivariable functions. So what even is a multivariable function? Well, it's in the name. It's a function that instead of only taking one variable, like f of x, you got a function that takes in two variables, f of x and y. And that, as a result, produces a z value. So what you can do with multivariable functions is you can plot them on the xyz coordinate. Right, so you can plot this on the x, y, and the z axis. So for a given xy coordinate, like a given xy point, well, it's going to correspond to some z value. So let's say at this point, which is like, let's say 1, 1, it corresponds to a height of, let's say 3. The height or the output z, you can say that's equal to 3. So I'm going to just give you an example of what I'm talking about. Let's say if I have this function, f of x comma y, let's say that's equal to xy. So we're just going to pick a couple of xy coordinates and let's see what happens. So I'm going to make a table here, and this is going to contain the x, y, and the z value. The z value is the same thing as f of x comma y, right? It's just the output value. When x is equal to 1 and y is equal to 1, well, 1 times 1 gives me 1. When x is equal to 2, y is equal to 2, well, then I'm going to get 4. When x is equal to 3, y is equal to 3, I'm going to get 9. When x is equal to negative 1 and y is equal to negative 2, I get positive 2. And you can see how basically any coordinate in the xy axis, so you can think about this as the xy plane, right? Where, this is your normal coordinate axis in the xy direction. And you pick a point, any point from this xy coordinate axis, and it maps on to a z value or a height, all right? So if you were able to plot all the points in our axis, right, you're going to get a specific shape. And let me actually show you what that would look like. So ignore this top thing for now. If I have f of x comma y, and let's say that's equal to xy, well, you notice how it has a really weird looking shape. You can see how as the x value and the y value, as they both increase, this kind of looks like a parabola. And that kind of makes sense from our values here, because we saw how as x and y increases, it starts resembling some kind of quadratic behavior, right? Because this basically, when the x value and the y value, so you can think about it as when the x value is just equal to the y value, well, then this function just becomes some x squared function. And that resembles that quadratic behavior that you see in the graph. Let's consider what's happening on this side right over here. Why is there a kind of negative quadratic behavior here, right? On one side, you have something that's positive, that's increasing, and then if you were to take a look at it from the other angle, you can see that it's something that resembles like a negative quadratic. X-axis, right? This is the x-axis, and then this is the y-axis. When the x value is increasing, but our y value is decreasing, well, then I'm just going to get a negative quadratic. And likewise, if my x value is decreasing and my y value is increasing, then we're also going to have a negative quadratic, because there's all of the x's here are going to be negative. So here's what I mean by that. So if our x value, you can say that if our x value is increasing, but our y value is decreasing, then we're going to get some sort of negative x squared function. But likewise, if our x value is decreasing and our y value is increasing, we get the same result. And we can show this, right? If our x value is decreasing, let's say if I go to negative 1, but my y value is at positive 1, well, then this just becomes negative 1. When my x value is negative 2, but my y value is positive 2, this becomes negative 4. And you kind of see the trend here. So this basically resembles a negative kind of x squared function. And the same thing would happen here, except the y value here is negative. Okay? So this is actually really weird, because it looks like at the coordinate 0, 0, right? It looks kind of like a minimum of this positive x squared function, but then it looks like the maximum of this negative x squared function. And that's actually called a saddle point. That's actually called a saddle point. A saddle point is really interesting because it's neither a minimum or a maximum. It's neither a minimum or a maximum. if you go in one direction, it'll kind of look like a minimum. But if you look in the other direction, it looks like a maximum. And so this is the weird thing about multivariable functions, is that now you're going to have these new cases pop up where the shapes are going to get a little more complicated and there's going to be a lot more. So now we're going to be graphing even weirder looking functions. And let's say that we have f of x comma y is equal to x squared plus y squared. And let's try to draw a sketch of this. So how do you think this is going to look like? Well, let's set the x value. Actually, let's set the y value. Let's say that y is equal to 0. When y is equal to 0, well then we just get x squared plus 0 squared, which is equal to 0. So when y is equal to 0, our function looks like x squared. So when y is equal to 0, our function looks like x squared. It looks something like that. Actually, let me do it in a different color. So it's going to look like x squared. And then if we set x equal to 0, and we're just going to get y squared. So when we set the x value equal to 0, we're just going to end up with a function that looks like y squared. And notice how at 0, 0, well, our z value, right, the result of this function is going to be 0, right? So we can write this as one coordinate on this function is 0, 0, 0, which is right over here. So the trick when you're trying to determine the overall or estimate of a shape of functions like these is you want to get a feel for how does something change along the x direction when I set the y value to a really nice value. And I can do the same thing for setting the x value to a really nice value and see the behavior along the specific axis. And I also like to find points that are just really obvious, right? For example, if I plug in 1 and 1 here, I know that my y value is going to be 2. So hence why if I go 1 in the x direction, 1 in the y direction, I'm going to get 2 up here. So it's going to form a kind of cup shape right over here. This would be how it looks like. Now, an important way for y'all to visualize these multivariable functions is something called slicing. So imagine if we were to graph this out, right? It would look something like a cup. Now, what if we set the y value to be a constant value? Let's say our y value was just equal to 1. Well, then if we set the y value equal to 1, then notice how on the xz plane, so on the xz plane, you're just going to have some variant of a quadratic. So when I set, let's say if we let y be equal to 1, then our function basically becomes x squared plus 1. And on our x, y, and z axis, right, we set the y value being equal to 1. And so our quadratic is going to look like some x squared plus 1 variant. Something like this. All right, let me draw this in red. It's going to look something like this. If we set our y value to be equal to 2, then we're just going to have x squared plus 4, right? Because you substitute 2 in here, you get x squared plus 4. So on the graph, if our y value is 4, then we're just going to get a quadratic that's going to be a little higher, right? So at right over here, we're just going to get a quadratic that's a little bit higher. And as we keep increasing the y value, you can think about it as our quadratic in the xz plane, right? The quadratic that's formed in the xz plane because our y value is held constant. It's going to keep increasing and increasing and increasing. So imagine if our y value is at a fixed constant. Let's say our y value is at equal to 1. Then we will have x squared plus 1. And notice how on our xz plane, right? Notice how this is a plane that contains essentially the x-axis and then the z-axis. So we call it the xz plane because it's like we're taking a slice out of our 3D function, right? A slice, aka a plane, out of our 3D function. And notice how that forms like x squared plus 1 behavior. And as I move closer to the origin, you can see that when our y value is equal to 0, notice how this just resembles regular old x squared behavior, right? And then as I move my y value to the negative side, it starts increasing again because, well, -1 squared is just a positive value, so we're just going to get a quadratic that's going to keep on increasing and increasing, right? We get a quadratic that's basically becoming higher and higher. So visualizing 3D functions with the concept of slicing them in some XZ axis or YZ axis, or I could visualize this using the YZ axis, which gives me this parabola. So the point is that slicing is a very important way for you to visualize what's going on in multivariable functions. I really want y'all to get a feel for graphing multivariable functions. We're just trying to sketch the general shape of them. So we're going to go over a couple more examples, and then we're going to experiment and plug in some cool functions that we probably can't visualize at first, or it's very, very hard to visualize. So we use Desmos or GeoGebra for those matters. All right, let's see if we can sketch out how this function looks like. Is there any way for us to do that? This is the x-axis, this is the y-axis, this is the z-axis. Is there any way I can visualize this? Well, let's say that x is equal to 0. We set the x value to be a constant 0. So that means that we're able to move freely in the y direction, right? Because we set the x value to a constant. So we're essentially forming a plane in the yz direction. Okay. When x is equal to 0, sine of 0 is equal to 0. So we're just going to get y to the third power. This might look something like this. We're going to get cubic behavior. Let's say that if we set y equal to 0, what do we get? If we set y equal to 0, then we're just going to get sine of x. So if we set our y value equal to 0, that means we're able to move freely in the x direction, but our y value is constrained to this value of 0. So hence, we're exhibiting sinusoidal behavior along the xz plane when our y value is constant. Let's say that x is equal to pi over 2. When x is equal to pi over 2, sine of pi over 2 is equal to 1. So this function is exhibiting y to the third power plus 1 behavior. So let's just say that let's see, this would be pi over 2. So at pi over 2 right over here, we would be exhibiting cubic behavior, except this is shifted up by 1. So you can imagine that this is going to be like a higher cubic function. And when you try to plot even more points and even more points, what you end up finding out is that on your xz plane, you basically just have a sinusoidal function. But when you plot things out on the yz plane, it just looks like a cubic. So if you were to plot the entire function, it makes sense that it would look something like this. Okay. How does this make sense? Well, if you were looking at it from the xz plane, so this is why it's called x-slice, when you're to take a look at a fixed y value, right? You fix your y value, you're fixing your y value to some value, and you're taking a look at when x changes, how does the z value change? Well, it just looks like a sine function. But if you were to look at it from the other angle, you hold the x value constant, so this time you hold the x value at a constant value, and you alter the y value, see how that changes? Well, it just looks like a cubic. Right? It just looks like a cubic the whole way. But notice how the cubic is constantly shifting up and down, because at the end of the day, it's also affected by the sinusoidal function, right? If you're at the peak of a sine wave, then your cubic's also going to be higher. And likewise, if you're at the bottom part, or the trough of the sine wave, your cubic would be at the lowest part. So having these two slicing views in mind really helps to visualize here. So all this time, we have been dealing with scenarios where usually you have the x value and the y value, and they're like separated. So it might be a little easier to tell what's going on with the function. But what if x and y are multiplied? You just do the same thing. If you let x be equal to 0, let's actually find out some easy points. So when x is equal to 0 and y is equal to 0, you just have cosine of 0. So therefore, our value in the z direction is going to be equal to 1. So I know that this point 0, 0, 1 is on the graph. What if we just set x is equal to 0 for the entire x direction, right? So if we have our x-axis, y-axis, z-axis, what if we just let x equal to 0 for this entire trip, right? We let x is equal to 0 and we move along the y direction. What do we get? If we let x is equal to 0, then no matter what the y value is, we can alter this y value as much as we want, but it's going to be a constant z value of 1. Because 0 times whatever this y value is always going to be 0. And likewise, if we let y is equal to 0, so if we let y is equal to 0 and we alter the x value, well, it's also going to be at z value of 1. So in both ways, we're going to get a z value of 1. If we let x be equal to pi over 2, what is that going to do? So instead of x being equal to 0, x is pi over 2, then you're going to have cosine of pi over 2y. Or actually, let's make this simpler. Let's say that x is equal to just 2. When x is equal to 2, you have cosine of 2y. So when x value is fixed to 2, you're just going to get cosine of 2y. So that might look, it's going to be hard to draw this, but something like this. And likewise, if y is equal to 2, then we're just going to have cosine of 2x. Meaning that in the xz plane, when we set our y value to be equal to 2, so this time we set the y value to be equal to 2, well then we're just going to have a little cosine in this direction. And what you'll actually find out is that if you just graph more and more cosines as you alter the x value, you fix it to some number, right? You're just going to get cosine waves with varying frequencies. And it turns out that this graph is actually symmetrical. Because think about it. If x and y were swapped, well then this would be cosine of yx, which is the same thing as cosine of x times y, since in multiplication, the order can be swapped, right? And so this function has a symmetry, right? Instead of f of x comma y, if this function was f of y comma x, it would still look the same. The x and y are just interchangeable. Hence, why when you graph this, I know this looks crazy, but it looks something like this. Notice how at the origin, right, we said how in both the x, the y direction, we're just going to have straight lines, right? Because it's at a z value of 1. But then, as I move the point around, right, to somewhere here, right, let's say this is a fixed, this right over here is a fixed x value, this right over here is a fixed y value, well then you're just going to get sine waves of varying frequencies depending on the point that you're on. Right? This is literally just sine waves of varying frequencies depending on where you're on. And notice how as you get closer and closer to the origin, your sine waves start becoming wider and the frequency starts decreasing. That makes sense because as you go towards 0, 0, then your frequency starts getting lower and lower, right? But out there, for very large values of x and y, if you were to shift this out to very large values of x and y, then when you hold one variable constant, it causes the other variable to have a very high frequency. Think about the case when x is equal to like 10, for example. Then in the y direction, we have cosine of 10y, which has a very large frequency compared to setting the y value to 1, for example. Therefore, the function looks something crazy like this, but I'm hoping that y'all understand why this function looks the way it is. Now, the rest of these multivariable functions, they're just for show, all right, to show you how crazy things can get. The first one is whatever this is, and it looks like ripples. So this is going to be symmetric because x and y are going to be interchangeable. It's actually going to be symmetrical about the line y is equal to x. Because think about it. When x and y are equal to each other, then the result of this function is going to be the same, right? When x and y are equal to each other, it's going to yield the same result. So this function, whenever x and y are interchangeable, the function is going to be symmetric about the line y is equal to x. What is this? What is this? This is like some kind of polar function thingy, except we're not using polar functions. What is this? It's like a 4-leaf clover. What does this one look like? Is this one like a egg carton? Or is it like a sheet? What do you think this one is? Comment down below, because I don't know the exact name for this function. What does it look like to you guys? And what the hell is this? What is this? What is this? Comment down below if you have a name for this one, because I don't. And I don't know what this one is. Now we're going to be talking about contour plots. Contour plots are just another way of simplifying how to view a 3D function. What if there was a way to turn a 3D representation of a multivariable function? What if there was some way to compress all of this information into just the simple x and y axis? Is there any way to go from 3 dimensions to plotting things in 2 dimensions while preserving most of the information? And the answer is yes. We use contour plots. So let's go back to our simple example. F of x comma y is equal to x squared plus y squared. Okay. Now I'm going to take a picture of this. Imagine if I wanted to find out all the z values. So I want to find out all the z values where that's equal to 0. Well, then it would just be this point at the bottom, right over here. If I wanted to find out all the z values that are equal to 1, that would be the equivalent of saying, okay, my z value here, let's say that's 1, right? Let's say this right over here is z is equal to 1, and I'm going to create a plane that slices through all the points. I'm creating a plane that slices through all the points where z is equal to 1. So the result would look something like this, right? It's all the points in our graph where the z value is equal to 1. And then if I want all the z values that are equal to 2, well, then I would just move up a height, right? All the z values that are equal to 2, if this is z is equal to 2, well, then this would be another ring, right? It's all the points in the graph where the z value is equal to 2, and so on, right? I can keep going higher and higher, find out all the z values that are equal to some integer in this case. So in essence, what contour maps do is you're basically setting the height of the function, the z value, to some constant, number. And based off of that, you're determining all the points where the function is that number. So it's all the points where your f of x comma y is equal to some constant, right? And so you see this using for mountain ranges or hills or valleys, right? When you're trying to represent geography, what people usually do is they use contours to actually sketch out all these rings where the z value is equal to something. In this case, the z value represents the height, or you can think about it as the elevation of our function, or this mountain range in this case. Okay? And you can project this to 2 dimensions, right? So here's an example in code where you have this function right over here. I did it as x squared plus y squared. It's the same one we've been using. And this is the contour in 3 dimensions. So you notice how you're basically just setting the z value to equal some number. And it creates these rings around the function where that's actually satisfied, right? All the points in our function where z is equal to 2 or 3 or whatever is satisfied. And then you can project this onto 2 dimensions using a color map. So based on how dark the color is, well, you see how the darker the color, the lower the z value is. So you can see around the origin, right, or even at the origin, that's where we have our lowest point where z is equal to 0. And as we move up this hill, right, as we move up this hill, well, it gets brighter and brighter, signaling that our function is starting to increase and increase and increase because we're going to higher and higher z values. Okay? In addition, how close the lines are, think about it, right? If we have a contour in 2 dimensions, let's say this is the x-axis, this is the y-axis. Let's say our contour looks something like this, where it initially starts out pretty far away, but then as you go further and further away, the contour lines become closer and closer to each other. The contour lines become closer and closer to each other. I know this isn't a really good drawing, but trust me on this. So let's say right over here, this is when z is equal to 0. Let's say right over here, this is when z is equal to 1, and so on. So every line that we essentially pass, we're increasing our z value by 1. Well, notice how if the lines are bunched up really close together, that means that if I move just a tiny step along this hill, well, then my z value, I'm increasing height really quickly, right? If I take a tiny step in this direction, well, my height's going to increase drastically compared to if I take a tiny step from the origin in this case, right? So if the lines are closer together, then that signals that the function is very steep at that specific moment. And the reason why is because it doesn't take much distance in order for your altitude to increase a lot. Okay? And once again, for these contour things, you usually want to give out like different colors depending on the altitude. So let's say this is red, this is green, this outer one is blue, and so on, right? You're going to assign colors so that the people looking at these contour sections are able to determine, oh, which one is in this section, which one is in this section, and so on. So they're able to differentiate all these different colors and different altitudes. Yes, I know this lesson is extremely visual, so I don't know if that's a good thing or a bad thing. I think that's a good thing, but this is another view of the contour lines for this function, x squared plus y squared. So notice how all these circles are essentially centered at the origin, and then as you can move further away from the origin, your altitude starts increasing drastically, right? The lines get closer and closer together, so you're increasing in altitude really fast. That makes sense because you're dealing with quadratics. The bigger the numbers, like you square a very big number, that's going to cause a huge increase in your height. So it makes sense that, well, there's going to be more lines, more and more and more lines that are closer together as you move further away from the origin. And there's actually how I did the contour map. So you just set x squared plus y squared to be equal to some value. Let's just say that's equal to a, and you let b be equal to 7. So b basically determines like how many lines you have, right? So if b is like 100, then you have a ton of lines. And so your a value, essentially this height of our function, is going to range from b, negative b, to positive b, meaning that we're letting the height go from negative 10 to 10, and we're seeing, well, when does the function reach, let's say, negative 10? When does the function reach negative 9, negative 8, negative 7, and so on? So we're essentially getting slices of our function, right? We're setting it equal to some constant height. We were taking a slice of our function, and we're seeing all the points that meet that slice criteria. Now we're going to talk about partial derivatives. But first, we got to review differentials. So what does a differential say? Differential basically says that a tiny change in y is caused by a tiny change in x multiplied by the slope. So if I move a tiny bit, let's say that dx right over here is approximately equal to 0.01, meaning that I'm approximately moving 0.01 units in the x direction. And let's say that my slope of this tangent line is equal to 2. Well, then my change in y is just going to be that slope multiplied by that change in x, which is 0.02. That's what the differential says, okay? And Also note that the idea of this differential comes from when you take the limit as delta x and delta y approaches 0, right? So the limit as delta x approaches 0, or sorry, the limit as x approaches 0 of delta x, well, as delta x becomes very, very small, so as the tiny change in the x direction becomes really, really small, that's going to give you dx, right? The infinitesimally small change in the x direction. And the limit as y approaches 0 of delta y is going to give you dy, meaning that as my change in height, so let's say I move from this point to this point, and let's say that causes some change in height. Well, as I move these 2 points closer and closer to each other, my change in y is also going to start to decrease and decrease and decrease to the point where it becomes an infinitesimally small change in the y value, dy. And if I take dy over dx, right, if I take delta y over delta x, right, the limit as delta y approaches 0 is dy, and the limit as delta x approaches 0 is dx, right? So what we can say is that, well, this is what the differential kind of stems from. It stems from the fact that a tiny change in y is equal to a tiny change in y over the tiny change in x multiplied by the tiny change in x. Because delta x is a very small number, you're dealing with actual numbers in this case. So you're not dealing with infinitesimally small numbers, meaning that if delta x is like 0.1, you have 0.1 on the numerator and the denominator. So it cancels out, and you get that delta y is equal to delta y, which is absolutely true, right? Because you're only dealing with changes in x and not infinitesimally small changes, this equation is actually true. But if you take the limit as these deltas go to 0, well, then that's where you get your differential from, right? Delta y turns into dy, delta x dx, and delta y over delta x, that's just dy dx. So the differential, you always got to remember this, but you can't really treat it like fractions. It just comes from the fact that when you take the limit as these deltas approach 0, that's where you get your result from. But the problem is when you're dealing with multivariable functions, so let's say that if this surface that I have right over here, let's say that's given off by a multivariable function, f of x comma y, well, notice how the output f, right? Notice how the output changes with respect to x and y. What do I mean by that? What I mean is that if I have a point on my surface and I move a little bit in the x direction, dx, that's going to cause a change in the height of my function, right? In this case, my height of a function, it looks like it's decreasing somewhat. So that's going to cause a change in the height of my function, df. But likewise, if I move in the y direction, so instead of dx right over here, if this was instead dy, right, if I move a little bit in the y direction now, right, move a little bit in the y direction, that also causes a change in the height of my function, which I'll also call df, because that's also a tiny change in the height. So notice how the output of my function df, right, that's caused by a tiny change in y, but it can also be caused by a tiny change in x. So what we mean by partial derivatives is that it's partial because you're only looking at like part of the picture here, right? If I'm taking the derivative of my function with respect to the y variable, right, partial f with respect to partial y, that's what it's called, right? These symbols are partial symbols, meaning that you're dealing with a multivariable function. All that means is that your function is changing with respect to multiple variables, and you're only looking at a partial view of what's going on. You're only looking at how does f change only with respect to the y value, right? You're ignoring the x value. You're only focusing on how it changes with respect to the y value. If you're looking at partial f with respect to x, well, what this is looking at is, hey, if I move my x value by a little bit, well, how does my output change as a response to that? Now, a lot of times, what you'll be asked to do is you got to find the partial derivative of f, let's say just with respect to x, and you want to find it at a specific xy point. So let's say this is the partial of f with respect to x at the coordinate 1, 0. Okay? And so the way you want to visualize this is that you're at the point, let's say 1, 0. So this is 1, 0. You're at this point, and if you move a little bit more in the x direction, how is that going to change the height of my function? Right? If I just move a little bit more in the x direction while keeping the y value at a constant value, how does that change my output? The reason why you keep the y value constant is because you're only looking at a tiny change in the x direction. You're not looking at a tiny change in the y direction. So you don't have to worry about changing the y value. You keep it constant. That's the whole point. So you only want to isolate the change in x. And if you want to isolate a change in a single variable for a multivariable function, then partial derivatives are the way to go. This is important because f, our function right over here, it can be affected by multiple variables, and maybe you want to see which variable has the most impact on the height, which variable has the least impact on a change in f for this function. So partial derivatives are very powerful for isolating changes for a single variable. So we can visualize this once again using our little cone example. So this is the x-axis, the red line is the x-axis, and the green line is the y-axis. And then, of course, that has to be our z-axis, the blue line. And notice how when I'm doing the x slice, right, so this is the xz plane, notice how my y value is at a constant value of 0, right? My y value is constantly, the green line right over here, it's at a constant value of 0. So we keep the y value constant, and we vary the x value, and we see how our function changes as a result of this. So you see how as I change my x value, right, as I change my x value while keeping my y value constant, you see that the slope keeps increasing, right? At the origin, my slope is 0, but as I move along the x-axis while keeping the y-axis constant, keeping the y value constant, our function keeps on increasing. So that is what the partial derivative of f with respect to x does. You keep the y value constant, you only alter the x value. And I can look at it from another perspective. Let's say that this time we're looking at the partial derivative of f with respect to y. So now we're forming the yz plane this time, and we keep the x value constant while our y value this time changes. And you can see that because this graph is symmetric, it's the same result. And here is both the views right over here visualized. As I move in the x direction, right, this is what it looks like. And then here's another view of that. So as I move in the x direction, you can see how both x and y, they're both changing, right? They both have completely different slopes. Isn't that cool? So that's the essence of partial derivatives. I'm going to say this one more time because it's super important. You only want to see how f changes with respect to one variable. So you keep the other variable constant, okay? And that's exactly what you do if you actually want to differentiate a function and find out its partial derivative. Let's say if you have f of x comma y. Let's say that's equal to x squared plus y squared. And you want to find out the partial derivative of f with respect to x. And sometimes it's also written as this, f subscript x, right? You sometimes see it like this. That's just a notation thing. It's the same thing. But what you do is you're going to differentiate x like normal, but all the other variables like y, you treat them as a constant. That's the important part. Because you're only moving along the x direction, so the y value, in all the cases, it's going to be a constant, right? You're not going to change it at all. So what's the derivative of x squared? That's 2x. The derivative of a constant squared, that's just 0. So the partial derivative of f with respect to x is just 2x. And we can do the same thing for y. This is also written as f subscript y. And if you differentiate x squared, right? Well, if you're differentiating with respect to y, you're only changing the y value, meaning that all the x values are treated as a constant. So wherever you see the x here, you're differentiating a constant, that's just 0. And the derivative of y squared with respect to y is just 2y. So there we have it. That's just how you compute partial derivatives. Whatever variable you're differentiating with, you do it normally, and all the other variables are treated like a constant. So I got Gemini to generate 3 problems for us to do, and we need to find partial with respect to x and partial with respect to y. So I think for this video, I'm just going to write it as f sub x and f sub y because it's simpler. So let's find out partial derivative with respect to x. So we're going to treat these y's as a constant. So essentially this can be rewritten as 4y squared, right? Because 4 is a constant and this y is a constant if you're differentiating with respect to x. And then this is multiplied by the derivative of x to the third power. And then minus 5 times the derivative of x. And then this is just a constant. So the 7y and then this minus 3 is just constant. So they zero out. And overall, try this out for yourselves. But you're going to get, this looks like 12x squared y squared, right? Because you do the power rule on this one. And then this term turns into minus 10x. And then these are just constants. If I find partial with respect to y, well, then x to the third power is treated as a constant. So I'm going to get 8x to the third power y, because I do the power rule on this y squared. That's just a constant. This minus 5x squared, that's a constant because there's no y's in that. 7 and negative 3 is a constant, so there we have it. This one, all right, let's do this one. Let's find partial with respect to x. Well, ln of y, if we're differentiating with respect to x, anything with this y right over here is just going to be a constant. So this is going to be 2x ln of y, right? Or sorry, yeah. So 2x ln of a y because this ln of y is a constant. And now you have to use the chain rule. So normally when you're differentiating e to the x, you would just get e to the x, right? But this time we have e to the xy. Now remember that y is treated like a constant. So whenever you have e to the, let's say 3x, right, it's going to be, if you take the derivative of that, it's going to be equal to, you differentiate it like normally, but then because of the chain rule, you multiply by the derivative of the inside function, which is just 3. So imagine if you instead had e to the yx, how would you do that? Well, you would differentiate it normally, and you multiply that by the derivative of yx with respect to x. So because y is just a constant, that's just going to be y. So overall, this is 2x ln y plus y times e to the yx, or e to the xy. Same thing. Final one. Quotient rule. Or sorry, I didn't do this one with respect to y yet. Okay. So differentiating with this with respect to y, x squared, all the x's are just treated as a constant. So this is just going to be x squared over y, because the derivative of ln of y is just 1 over y, plus, and then this is going to be the same thing, right? The derivative of e to the xy, that's just e to the xy, times the derivative of xy with respect to y, that's just x. And finally, the quotient rule. So let's take the derivative with respect to x first. So this is going to be the bottom times the derivative of the top, which is 2, minus the top times the derivative of the bottom. So the derivative of the bottom with respect to x is going to be 1, right? Because the derivative of y with respect to x, that's just going to be equal to 0. So you're just going to get 1, and 2x times 1 is just 2x, all divided by the bottom squared. So this is just going to be equal to, this looks like, what, 2x plus 2y minus 2x. 2x's cancel out, of course, over that. So you just get 2y over x plus y squared. And then partial with respect to y. Well, this 2x then can be treated as a constant, right? So this is going to be 2x times the derivative with respect to y of 1 over x plus y, right? Because this 2x can be treated as a constant since you're differentiating with respect to y. Well, I can rewrite this as x plus y to the negative first power, right? This is x plus y to the negative first power. So from the chain rule, right, you bring the power down, subtract 1, and then you multiply this by the inside function with respect to y. Well, that's just going to be 1, so it's going to be 2x multiplied by negative x plus y to the negative second power, aka negative 2x over x plus y to the second power. And if you want to evaluate, let's say, this at the point 1 comma 0, right? So if x is equal to 1 and y is equal to 0, well then you just plug everything in here. So that's going to be negative 2 divided by 1 plus 0 squared. So that's just going to be negative 2, right? But the point is that you got to get comfortable with taking partial derivatives, all right? And realizing that a lot of the things, x's and y's, can be treated as constants. So this is the limit definition of partial derivative. What this is saying is that if we keep the y value constant, but the only thing that we change is this x right over here, right? Instead of just regular old x, we have x plus h. So we're changing x by infinitesimally small amount, right? How is that going to affect our output, right? What's the change in output? And likewise, if I were to do the same thing for partial with respect to y, it would literally be the exact same thing, except this is partial f with respect to y, and this would be the limit as h approaches 0. But this time, what do you think is going to happen? This time, because you're doing it with respect to y, you're changing the y value by a little bit, and you're keeping the x value constant. So this is going to be y plus h minus f of x comma y. So notice how y is the only thing that changes when you're doing this limit. In the next video, we're going to cover the total differential. So is there a way that I can write the change in f as a differential in terms of these partials? And we're also going to view how to write out the equation of tangent planes and a little bit of an intro into optimization problems.